Great. I'd like to thank the organizers for a wonderful conference and for inviting me to come here. I especially thank them for having it just be 5 minutes from my house so that I could walk over here every day. Today I'll be talking about a number of measurements: the proton size, measured by the Lamb shift in hydrogen, the fine structure constant, measuring the 2-triplet P fine structure of helium, and about a new venture that we're doing to measure the electron electric dipole moment. Yep. There we go. And of course, I'd like to thank very generous funding sources that have helped us to be able to do these measurements. So I'll start with the proton size. This story goes back to 1956 when someone wrote an article. Two people wrote an article in Physical Review suggesting that if you measured the 2s1/2 to 2p1/2 Lamb shift in hydrogen, you should be able to see the effect of the proton size. This, by the way, is the whole article, and if you look back in the archives, there are a lot of articles of this sort of length back in the day. And so wouldn't it be nice if you could write a one-paragraph article these days? Of course, the key is that there's some probability that the electron is going to be inside of the proton, and when it is, well, the probability is about the volume of the proton divided by the volume of the atom, at least for S states that penetrate all the way in. And so the electron, when it's inside the proton, doesn't see the full proton charge, and so it doesn't see a Coulomb potential. It sees a modified Coulomb potential, and they got the answer right. The effect is about 0.1 megahertz. So here is the n equal 2 energy levels. The difference between the 2s1/2 and 2p1/2 is much bigger than this 0.1 megahertz. It's about 1,000 megahertz, and that's because of QED contributions. And I'm just giving a few random diagrams here to show that. But the QED contributions have been calculated. This is a whole list of them, I believe. And this is not controversial. This is all completely understood. Everyone agrees on this. People have been calculating this for over 5 decades. No one is thinking any of this is controversial. Its uncertainty is down below the part per million, which allows one to measure the Lamb shift and get a better than 1% measurement of the proton size. So this was life back in most of my life up until 2010. We knew what size the proton was. CODATA told us every time on those little cards what size the proton was. And then in 2010, someone measured the muonic hydrogen Lamb shift, and there was a different value. There's a very, very small uncertainty to this, and so there was a 7 standard deviation discrepancy between the accepted value and the new value. And so that got a name, the proton size problem or the proton radius puzzle. People started to wonder whether you would get a different radius depending on whether you measured with muons or with electrons. Were there some new physics that was causing this problem? So before we were able to finish our measurement, there were 2 new measurements, but one of them agreed with the small radius and one agreed with the big radius, so we still got to be the tiebreaker when we finished our measurement. So what are we doing? We're measuring, of course, the 2s1/2 to 2p1/2 interval. In particular, we're measuring this fine structure interval. We're doing it by starting with 50 keV protons. We charge exchange with well, we could use any gas, but we use H2 gas because it's slightly better than other gases. 50% of them neutralize. They're going at about 1% of the speed of light. And about 4% of them end up in the metastable state, and those are the ones that we use for our measurement. We deflect out the protons, and then we get rid of the state we don't want. We get rid of all of these F = 1 states. The P states disappear immediately because they have a lifetime of 1.6 nanoseconds. And now we have only population in this state. So we drive a transition down from this to the short-lived P state, and we use separated oscillatory fields for this. So here are two separated regions that are going through two RF waveguides, actually. And then after that, we again empty the F equal 1 state to make sure that it's not polluting our signal. And we send this into a detector. In the detector, we apply an electric field. The electric field mixes the 2s and the 2p state. That quenches the 2s metastable atoms, gives off a Lyman alpha photon, and we detect that in a gas detector. We're using this brand new technique called frequency offset separated oscillatory fields. So rather than having two regions that we run at different phases, we run them at slightly different frequencies. Well, that's the same as running them at different phases, because the one is catching up, is always getting ahead of the other in phase. So we're just continuously scanning through all possible relative phases. So there's a very small offset that we use. And then what we do is we look for a signal at the beat frequency. So in fact, that's exactly what we get. This is our Lyman alpha detection signal. And here we have constructive interference. This is quantum interference in real time. You can see it on a scope. You get constructive interference. You're killing all of your 2s atoms here. And destructive, you're not killing any of your 2s atoms there. And then here's the beat frequency. We just beat the frequency of these two together, and we get this. And the beautiful thing is that these two things should be exactly in phase if we're using a microwave frequency that's exactly equal to the frequency difference between the two atomic states. So as the atoms go from here to here, they're developing their phase according to F0, and in the same time, the microwaves are developing their phase according to F, and because of that, these two should be in phase when we're in resonance, and that's all we're doing for FOSOF. It's critical that we really know the relative phase in these two regions, and that's hard to do. And so we sort of go to heroics for that. What we do is we just take these two regions and we exchange them. So it's tempting to exchange them by exchanging the cables that go to each of those regions, but that's not good enough because cables aren't good enough to preserve the phase when you take them off and put them back on. So what we had to resort to is rotating the entire RF system. So we put a big 18-inch rotational feed-through here into our vacuum. We put all of our RF components inside of this box, temperature stabilized it, and then everything, including the regions, the amplifiers, the generators, everything got rotated without putting any stress on any cable as we did it. So here we are rotating it. Usually we don't have our vacuum open when we do this, but it made a better picture that way. And then if we have it in the other rotation, now these two regions have been inverted. So any phase error that happened here, delta phi, is inverted here because we've seen, now they're seeing them in the opposite order. So this is the line shape we get. From the red curve we get, as a function of RF frequency, this is the phase difference between the beat signal and our Lyman alpha signal, and for the blue one, it's this one here. Where those two cross, that's the resonant frequency. So another way to do that is to average the minus the 0 degree one and plus the, when you've rotated it 180 degrees, and you get this line shape. So it's a nice line shape. It's basically a straight line. It cancels that effect of not knowing exactly what the relative phase of the two RF regions was, which is related to how long the cables are going to those regions, whether there are any things that cause phase delays. And then this intercept tells us what our line center is. That's all we have to do. This fits well to a straight line. We spent We burnt up years and years of CPU time modeling this line shape, and the years and years of CPU time also was consistent with a straight line. Here are the residuals to that straight line, and this is 90 minutes of data, and it has a statistical uncertainty of 2 kilohertz. So that was what we aimed for. We wanted 2 kilohertz. So we were pretty happy that 90 minutes in, we were good. So we took 6 more months of data. Because this is a brand new technique, we wanted to make sure that we got the same answer regardless of what parameters we ran at. So we did more severe parameters where we put the regions far apart. We lose signal as 1 over E for every lifetime apart we put them. We went to small electric fields to reduce the AC Stark shifts. We changed the speed of the beam. In the end, we had a statistical uncertainty of 0.5 kilohertz, but we were limited by systematic effects. The largest systematic effect is time dilation, but it's easy for us to measure the speed of our beam, so that wasn't really a big problem. We got a 1 kilohertz uncertainty on that. And we checked by running at slower speeds, and we got consistent results even when that time dilation correction was a factor of 2 or 3 smaller. And then the AC Stark shift was a big one. This is just the shift due to the RF field itself. Here, there's no simple formula for what the AC Stark shift is for FOSOF. The only thing we could do was numerically integrate the entire system. We did that for all 400 elements of the n equal 2 state, and we integrated just from the very beginning of our experiment to the end of our experiment, and we put in, so that's 700 nanoseconds of integration, and we numerically calculated all the fields along the way, and then made estimates of all the uncertainties and reran this with all possible range of fields that we thought could be possible. The modeled shifts ended up between 5 and 155 kilohertz. If we went to low powers and large separations, it became small. And we found that our data followed exactly the pattern of the modeled shifts, at least within 5%, which is how accurately we measured it. So here are our results. We took measurements with different field strengths, different speeds, different separations between our regions. We did our analysis blind. We unblinded 10 days before we originally submitted this. And we got consistent results. In the end, we had a 3.2 kilohertz uncertainty, of which most all of it was systematic, 2.3 kilohertz from the AC shift itself. 1.5 kilohertz, still on being not entirely certain that as we rotated this thing, we were keeping the same phase. So we measured that in 3 different ways to make sure that the phase didn't change as we rotated the whole thing. But we could only prove to ourselves at this level that we'd done well. So here we are. We broke the tie. We agree with a small radius. Since that time, there have been some new measurements. There was an electron scattering measurement that also was at the small level. From Garching, there was a measurement of the 1s, 3s interval. And most recently from Colorado State University, a measurement of the 2s, 2d interval, which is starting to, open the controversy again, I guess. Okay. Let me just keep moving then and talk about also the helium fine structure measurement. Here we're doing quite a different experiment in that we're using a thermal beam. We're using a metastable beam that we concentrate using a 2D MOT. We get a very intense beam going through. We laser excite from the metastables that we get from this discharge here up into the 2p state. And then we drive transitions between the 2p intervals, and we can get near unity detection efficiency by exciting up to a high end state and then ionizing. So we get incredible signal to noise on this thing. So again, we're using this FOSOF method, And we really have tested the Fosoff method well here. As I say, exceptionally good signal to noise. In fact, we could do experiments that span 10 lifetimes and just take the factor of e to the minus 10 loss in signal and still get a good measurement. So that's our straight line Fosoff line shape. If you take the straight line out and expand by a factor of 100, you see that it's not quite a straight line, but this is exactly the predicted thing that you get just using standard SOF line shapes. So that this is a fit to the expected line shape, but this is the expected line shape. And then if you expand that again by a factor of 100, yeah, you can see the residuals are good. So just incredible. I've never had this good of signal to noise in my career so far before this. The great signal to noise allowed us to do a lot of tests. We changed a lot of parameters, B fields, the length of the interaction, the time between the interaction, the separated fields, saturation parameters, M states, laser parameters, and so on. We could and this is just a partial list. We just tried to turn on or off or down every knob we could in the lab, and we couldn't seem to get this number to change. So in the end, we were able to get a 25 hertz measurement. That's of the small interval. Really, to take advantage of it, we need two things. We need to do the large interval, which is what we're in the process of doing, using the same technique now. And we need, if there are any QED theorists in the audience, we need the next order of QED theory. Krzysztof Pochucki is considering that at this point. So, if we put that all together, we'll get a part per billion test of QED in this 2-electron system. It will test for the possibility of exotic spin-dependent electron-electron interactions at 100 times higher accuracy than has been done before, and it'll lead to a 0.5 part per billion determination of the fine structure constant. And of course, that can be compared, as we've heard in previous talks, to G-2 and to atom interferometry. I mean, the game here is to see whether we get the same value of alpha from all measurements, because if we do, we understand all the physics. If we don't, then either there's physics beyond the standard model, which would be great, or we are going to have to go back and make sure that we're not making an error in our measurements. And you can see a poster on this this afternoon. Okay, and finally, I'd like to talk about our new venture, measuring the electron-electric dipole moment. So EDM cubed is what we call our collaboration, electric dipole measurements using molecules in a matrix. And so what we're doing is putting barium monofluoride molecules, we're freezing them into a cryogenic solid. So we're freezing our beam of BAF basically into a solid so that we can keep it and use it for a long time. What we'll do is we'll have a very large number of BAF. I mean, our first measurement will probably have about a 1 millimeter cubed of solid argon, and at 1 part per billion of barium monofluoride to argon. And that already gets us 10 to the 10 barium monofluorides that we can use in every measurement. So that has the potential of giving us just incredible signal-to-noise statistics on it. A benefit is that the molecular orientation is fixed by the matrix. There's no need to apply an electric field to fix the direction of the BAF. And at least known systematic effects are quite favorable. I mean, if you think about the sort of systematics that the current EDM measurements have, it's great to have a small volume, it's great to have them cold, it's great to have them stationary. Of course, we may find some systematics that others don't have to deal with because we're inside of a solid. If you look at statistics and the hope for the systematics being small, you would imagine we might be able to decrease the limit of the electron-electric dipole moment by 3 to 5 orders of magnitude. just with a cubic millimeter of solid argon. So what does BAF look like when it's inside of argon? Well, argon is just an FCC crystal. If you look at FCC, just if you look at one argon atom, it's got 12 nearest neighbors, all at the same distance, and they form this structure if you look along the 1-1-1 axis of the crystal. And what happens with BAF is it replaces 4 of these argon atoms in exactly this, thank you, in exactly this way here, the center one and the equilateral triangle at the top. And the BAF is perfectly aligned along the 1-1-1 axis of the crystal. And we're fortunate, because we didn't know this before we started, but the BAF fits in this spot. That is to say, it doesn't have to push the argons out. All the argons, all the ones that haven't left, stay where they were to better than 1/10 of an angstrom. So there's not much tension in having the BAF at this location. How do we know this? Well, we've done some serious calculations. We start with calculating the triatomic molecule for 1,400 different locations of the argon. And so we do all electron relativistic calculations. We include correlation. We extrapolate to full basis sets. We do a serious calculation. We have physical chemists on board to help us with this. And that effectively gives us a potential of how much energy does it take to have an argon here or here or here. And if you put that together with the argon-argon potential, that's well known, you can start to just look at a cluster of argon atoms plus 1 BAF, minimize the energy of that whole cluster. The outside of the cluster you force to be at the crystal, where the crystal is, and you can just find out what the structure looks like. So again, that's a fair amount of work to do that. We've burnt up some computing time for this. But what we find is that it's very clearly wants to be substitute for 4 argons. It's a 50 millieV difference for substituting for 3 or 5 or any other number. And 50 millieV is huge in this game. I mean, at 4 Kelvin, KT is 0.3 millieV. So it's very, very strongly favoring this substitution. Also, if you look at what happens if you try to tilt the BAF away from the 1-1-1 axis, you get many millieV of energy that it takes to tilt it. So 60 millieV to tilt it over to the next direction that it might want to go in. And again, that's just not going to happen at the 0.3 millieV that's available in our solid. If you ask, can you move this from a location to another location, again, it's in a well that's well over 50 millieV deep. At 4 Kelvin, in fact, the barium monofluoride will be in of course, it'll be in its ground electronic state. It'll be in its ground vibrational state. You'd think it might be in its ground rotational state, but there aren't rotational states because this thing doesn't allow it to rotate. So instead of rotating, it can only librate, and it'll be in its ground librational state. And of course, it can move around, but it'll be in its ground motional state as well. So the only levels that can be populated are the 4 hyperfine levels associated with all of those ground states. Those hyperfine levels are just the electron spin up and electron spin down and nuclear spin up and nuclear spin down. This is just the hydrogen atom again, right? This is the ground state of hydrogen. Why is this displaced? Well, this is exactly what happens to hydrogen if you put it in a huge electric field. The matrix gives shifts that are very similar to having a large field, because the shifts due to a large Stark shift are really about orienting the molecule, and that's what this is about as well. But here we don't have to apply an electric field because the matrix orients the molecule all by itself. The measurement sequence that we use is the same as it would be for a beam of molecules. And I mean, optical pumping, we set up a superposition, we let it precess, and then we read out the superposition at the end, and we detect with fluorescence. We'll simultaneously be looking at both upward and downward pointing BAF molecules, and we will separately read out each of these by, during this whole time we'll have no electric field, but here we'll put on an electric field, and the electric field will shift these guys differently than these, because these will become slightly more contained, and these will become slightly less contained. In one case, the electric field is working with the containment that's happening by the matrix. In the other case, it's working against it. And so you get a very subtle shift here, but with RF transitions, we should be able to separate out those two. There are actually 6 other directions. I mean, there are 8 directions in all that are all symmetric here, but the other ones will have different shifts, and we won't address those at all. So we've made a laser ablation buffer gas source. We've shamelessly copied what Mike has done for that, and it worked on the first go, so we're happy about that. We get 10 to the 10 barium monofluorides with every laser pulse, and we have a laser that can pulse at 100 times per second. We can see that in laser absorption. More importantly for us, we can see it in a residual gas analyzer, because we don't want all sorts of crap going into our argon solid. So we don't want to just look at how much BAF comes out here. We want to look at how much of everything else comes out as well. So we can produce transparent solids. We're implementing methods to improve and measure the purity and make large single crystals. And what we intend to do with these BAFs is to deflect them so that we don't get all of that crap onto our argon. And so we've come up with a method using absorption and stimulated emission that allows us to get 2 kicks every 10 nanoseconds of 2 photon kicks every 10 nanoseconds to give a very hard push onto these molecules. And you can look at the details at a poster this afternoon about that. And we're also looking at a nice mirror that we can make where we can get specular reflections off of positive and negative wires that are going across here. So again, you can look at a poster for that. And so that's all I really have to say. I should mention these are the people who really did the work. We're looking at a bunch of great students and postdocs and collaborators, and we're looking for other people to join us. And thank you for your attention.
Okay, great talk. Perhaps we should pick up the online question first. This time, okay. Why there's a large disagreement in terms of standard deviation for different measurements? Is it possible that the electronic state is indeed modeling the effective proton radius?
Yeah, so I mean, my standard answer to this question, because it's always the first question, is I spent 10 years measuring the size of the proton, and everyone wants to ask me about other people's measurements of the size of the proton. I can't defend everyone's measurement of the proton. The true answer is that these are extremely difficult. Like, we're pushing these measurements too hard. I mean, that's why I started doing this measurement in 1980 when I was an undergrad. And I realized for many, many decades that this is too hard to do and we shouldn't try to push this hard. And so there was a reason to push this hard and we did it, but man, it is really hard to get all the systematics under control for measurements at this precision.
Here? Yeah.
Yeah, thank you. I may have a very naive question.
Let me just, I don't mean to say that about other people's measurements. You know, we're the stupidest people here, right? We used the shortest lifetime state. Like, we want to know where the 2s is. So we went to the 2p, which is the shortest lifetime state in hydrogen, rather than to long-lived states. So, you know, we did the hardest measurement we could.
But it's solid. They all come in solid.
Sorry,
Okay.
I didn't mean to interrupt.
Yeah, thank you. Yeah, I have maybe a very naive question. So I assume people call it proton size puzzle because it's unexpected, it's a surprise. I guess my question is why people think like the interaction, for example, between the proton and the electron and the interaction between proton and the muon will change the size of the proton?
Yeah, and you know, they never should have, right? I mean, no one really came up with a good theory that could explain that. So, you know, we've just done, as a community, we've done enough precision measurements now that, you know, you know, a lot of the theories that people came up with were, you know, exotic things involving muons. And ironically, almost all of them got shot down by the fact that G-2 muon is at least approximately equal to theory. I mean, there's that discrepancy, but all of the theories, you know, just would have had it out in left field rather than just a small discrepancy. So there really was no real going theory that allowed the muon to, but there it was, 7 standard deviations. We had to resolve what's going on. So I guess we never know what it is until we finish doing the experiments.
Maybe a really quick question, actually. What actually is the real, I mean, how to say, the definition for proton size?
Yeah, so this is the RMS charge radius of the proton. And so that's the simplest way to think of what it is. So it's easy to think from the point of view of an atom. That's exactly what we're measuring. If you do the calculation of how the Coulomb potential is affected as you go inside the proton, it's just the RMS radius that makes the first order effect anyway. I suppose eventually there's quadrupole sort of things. So that's the definition, the RMS charge radius.
Thank you.
Yes, over there on your left. Here. So about the EDM, so it sounds like a wonderful way to get lots of molecules into a small space to use a solid as a matrix, right? And so then we could think of, like, why don't we do that for like every measurement we want, right? Why don't the clock people put like strontium atom inside argon lattice and then measure that, because it would get much better statistics. And so I guess I would say that the interactions with all the electrons around would like shift your transition in a way you don't want it to. And I would like to know why, in your case, it is not affecting too much. You've explained very well why the molecule stays where it is, and it's sort of like locally in its ground state of the trap. But I guess the entire solid is not in its motional ground state. You still have phonons going through it. And so I guess you still have like the distance between the other argon atoms getting changed by those phonons, and why does not that affect the measurement?
Yeah, I mean, there will be effects. I mean, fortunately, the effect on this guy will be identical to the effect on this guy, unless there's something else happening as well, right? So, and so the other thing that could be happening, you know, could be impurities in the crystal or imperfect crystals, or so in the end, it's really a technical issue. How well can you make a perfect argon crystal? If they are perfect, you know, we don't care what the frequencies are here. We just care whether this one acts exactly the same as that one. And in all ways, they're identical, except for that the electron has a reversed electric field compared to a magnetic field, which I didn't put in here, but we'll put a magnetic field in one direction. So one will reverse the electric field versus the magnetic field, and the other one won't. Yeah, so I mean, I guess we don't care either what the frequency of a strontium transition is, maybe, but one thing to say is that, you know, one of the reasons this works so well is that it is a molecule. This thing gets fixed in this spot because it's hard to move a molecule around inside of one of these. Atoms move much more easily. And I think we as a community got discouraged about doing measurements in matrices because of the fact that, you know, alkali atoms, they just move all over in the matrix. They find defects, and it becomes very complicated to do things with atoms in matrices. So molecules are way better because they're just they're held in place. They have little pinchers holding them in place, basically. But yes, you know, we'll find out what the systematics are associated with, and how, you know, whether it's going to take years or decades to make it perfect enough to be able to do a measurement here. That's something that we're just going to have to figure out.
Okay, I think the next question from students. Yeah, microphone, please.
Hi, great talk. Just a question about this scheme that's on the slides. I would naively think that it's very important that the electric field that you're applying during your readout stage is aligned with the crystal axis of your crystal. I guess 2 questions. Is that actually a necessary condition? And if it is, how do you experimentally achieve that?
Yeah, I mean, we have some evidence, or there is evidence in the literature that since we grow our argon on sapphire, that it does actually grow with the 111 axis perpendicular to the sapphire substrate. So that just means that we apply an electric field that's perpendicular to the substrate. But we don't need it to be exactly perpendicular. We just need these one to move upward and the other one to move downward. So even if we were 10 degrees off on that electric field, we'd still shift these things out. So it's not a critical number there.
Well, question. I think, yeah, Professor Metcalf. Yeah.
You made a comment about some technique that you developed to impart 2H bar K in a single shot. Could you comment quickly about that?
Yeah, I mean, we were inspired by this guy, Hal Metcalf, who did this 2-color thing where you tried to get, where you tried to get a kick going up and a kick coming down. So we tried the 2-color, and it didn't work very well for our system with molecules here. And you know, it's not easy to do this either. We have to do this in a 1 kilogauss field so that the states are not degenerate with each other, so that we don't pump things into dark states. We had to do a serious density matrix calculation on this. But the beautiful thing is that since you're kicking them up and kicking them back down, sometimes these happen out of order, but the spacings between here put you back in order. You'll have to come to the posters to talk more about that. But because you're mostly pumping up and pumping back down, there's very little spontaneous decay. And because there's little spontaneous decay, you don't get stuff going to all the other molecular states, like the V=2 states and V=3 states. You don't get it going to other rotational states or through the delta state. So we still need 1 repump laser, but we don't need a whole slew of repump lasers because we've basically gotten rid of 90% of the spontaneous decay.
Are these separated in time? How do you get them to be in the right order?
Yeah, they're separated in time, yes. So they're 2 nanosecond long pulses, a pair of them, one coming from the downward direction and then immediately one coming from the upward direction.
Very quick question.
Question will be quick. I don't know about the answer. So I didn't really catch what the key advantage of doing the frequency offset SOF, and why doesn't everybody do it?
Well, everyone should do it. I mean, I really do believe that. It's so what's the key advantage? The key advantage is that at least if you're doing these sorts of 2 regions, switching between 0 degrees and 180 degrees is something hard to do, well. You're hitting the system and because you're hitting the system, you're changing the phase of the microwaves as they're going to your system, basically, right? It's got to go through some magic T, something, but something's going to warm up, some path is going to lengthen. It's hard to control. And this, the way we're doing this, it's just, it's continuous. So it's kind of like doing a continuous SOF experiment. And yeah, people should have thought of it a long time ago. We couldn't believe when we thought of this that it wasn't something that people had thought of a long time ago. We searched the literature and were surprised.
So basically it makes it easier to get that phase shift exactly what it's supposed to be because
That-
you've got a way of testing that.
That's right, yeah.
Yeah. Okay.
And there's no, you don't have to go between different setups, basically, to do it.
Okay, I think we should stop here by thanking